Since last time we already discussed about the density curve, you are ready to go into the main details of this chapter, normal distribution and standard normal distribution. So first, we want to know what is normal distribution. Graphically speaking, a variable is said to be normally distributed or to have a normal distribution if its distribution has a shape of a normal curve. For a normally distributed variable, the percentage of all possible observations that lies within any specified range equal to the corresponding area under an associated normal curve. Does that sound familiar? Yes, it sounds just like the density curve that we discussed in last section because the normal curve is just a special case of a density curve. The result also holds true for a variable that is approximately normally distributed as well. You will see this distinction in examples to come in this chapter and in the following chapter since there is some differences between a normally distributed and approximately normally distributed variable. First, the normal distribution has a probability distribution formula as given here. Fx equal to 1 over square root of 2 pi times sigma e to the negative x minus mu square over 2 times sigma square. It looks quite complex, right? So if you know calculus, you can know that finding the area under the curve is the same as integrating some definite integral. But we are just introducing this formula here. You don't need to know any calculus or do any integration. Also, a reminder, there are two Greek letters that you have seen before. One is mu, that one, the letter look like a U. You have seen this as a symbol of population. And sigma, the letter that looks a little bit like number 6, that you saw it back in the previous chapter is population standard deviation. So this formula looks quite complex and you indeed cannot integrate it and get a closed form expression. So we don't have to pay too much attention to complex approaches. So here I introduced it as the way for you to see how a normal distribution can be represented in formula form. Okay, where mu is the mean and sigma is the standard deviation of the distribution. So we mentioned about the normal curve. What is a normal curve? The normal curve is a curve that satisfies some of these properties. Actually, I have three of them. The first one, the curve is bell-shaped, center at, and symmetric about the mean. Property 2, the total area under the curve and above the horizontal axis equals to 1. Property 3, close to the horizontal axis, outside the range from mu minus 3 sigma to mu plus 3 sigma. So I also introduced a graph here so you can see it visually. This is a picture of a normal curve. So you can see that the first property can be seen quite clearly on the graph with the center at the mean mu and it has a symmetric bell shape. Properties 2 is the same as that of a density curve. The total area underneath the curve and above the horizontal axis will be equal to 1. So you can see mu plus sigma, mu minus sigma, mu plus 2 sigma, mu minus 2 sigma is symmetric. Mu plus 3 sigma, mu minus 3 sigma. Okay, and property 3 simply means that on the two directions, from the positive direction, negative direction, the two tails, the area gets really small since the tails get very close to the horizontal axis beyond the points of 3 standard deviation away in either direction. So here we have the normal curve. Usually people denote the mean and the standard deviation next to the normal curve. So any curve that satisfies these three properties we discussed above will be called a normal curve. And in turn, any variable that has a normal curve will be called a normally distributed variable. Now that you know what is a normal distribution, what is a normal curve, let us focus our attention on a special case of the normal distribution, which called the standard normal distribution. So a standard normal distribution is a normal distribution with mean 0 and standard deviation 1. So any normally distributed variable can be standardized to have the standard normal distribution. And I will discuss how in a little bit. So the graph above will change a little bit, slightly, for 0 substituted for where you have mu before and 1 substituted for where you have sigma before. The same goes to the formula you saw. So any distributed variable can be standardized to have the standard normal distribution by a formula we would discuss. So the standard normal distribution has the probability density function given as f of z equal to 1 over square root of 2 pi e to the negative z squared over 2. People usually use z because of a concept called z-score, which I will discuss in a little bit. I also include a graph of the standard normal distribution here so you can see. So instead of having mu in the middle, now you have 0. Okay, then you have 1 because why? Before you have mu plus 1 sigma. So you have just 0 plus 1, so it becomes 1. Likewise, you can have negative 1, 2, negative 2, 3, negative 3. And all the property before still hold. And this is called the standard normal curve with 0 and 1. So what is a standardized, how do you standardize normally distributed variable? We do so by utilizing z-score. The standardized version of a normally distributed variable x is usually denoted as z, and z can be computed using this formula, z equal to x minus mu over sigma. And some of you have seen this formula introduced in previous chapters before, so here is a little bit of a recap. So the z variable here will have a standard normal distribution. The z values calculated before is usually called the z-score. So standardizing normal curves. So here I start with a normal curve. I have A and B is any two number enclosing the red area of interest, the shaded area. To standardize this normal curve to be the standard normal curve, I can use the formula we discussed above, z equal to x minus mu over sigma. Now I can have the standard normal curve. So the two values a and b, now they also change to be a minus mu over sigma. Just substitute the value where x was at, and then b now becomes b minus mu over sigma. So from a normal curve mu sigma from the left, now I have the standard normal curve 0, 1 to the right. So the red area enclosed in between, even though the shape changes a little bit, they are the same. They remains the same. The area does not change. The area enclosed is the same, even though the shape is transformed. That is how we standardizing normal curves. Equal areas, as you can see. So just like normal curves, the standard normal curve also has some properties. Property 1, the total area under the standard normal curve is 1, not surprisingly. Property 2, the standard normal curve extends indefinitely in both directions. It approaches but never touches the horizontal axis. It gets very, very close to a horizontal axis, so sometimes people think they touch, but they don't actually touch. Property 3, the standard normal curve is symmetric about 0. 0 is also the mean of the standard normal curve. Property 4, almost all the area under the standard normal curves lies between negative 3 and 3. Why do we want to study standard normal curve? We do so to be able to use what is called the standard normal distribution area table to find the area under the standard normal curve. Since we can find the area under the normal curve, we can find the probability we are interested in. for any normally distributed variable, which are very common in practice. Here I include some illustrative graphs in finding the area under the standard normal curve. Just like before, in the section where you learn about density curve, you can see that z can be any value, and the shaded red area is the area to the left of z. Here z can be any other value, the shaded area to the right of z. So to find the area to the right of z, you just simply use 1, the total area under the standard normal curve, minus the area to the left of z. And then you can have any two values of z, z1 and z2. To find the area in between z1 and z2, the shaded red area, you just use the area to the left of z2 minus the area to the left of z1. And we can do so by using a standard normal distribution area table that I will introduce to you in a little bit, also provided by your textbook. Using the standard normal table, so the area under the standard normal curve is usually tabulated to 4 decimal places in the body or inside of the standard normal curve table. The outer columns and rows are the z-score. Usually they are reported to 2 decimal places. Typically, area under the standard normal curve in such tables lie to the left of any specified z-score. I will show you how to look into a table in a little bit. Usually, it's tabulated in 2 separate pages. One page, the first page, has negative z-scores. The other page, the second page, has positive z-score. In this discussion, we will use table that ranges from z equal to negative 3.9 and z equal to positive 3.9, because area to the left of negative 3.9 or to the right of positive 3.9 are usually very small and is quite negligible. So to use the table, we first go down to the column to look at the z-score, then go to the right or to the left of the rows. Once I introduce some example, if you are still confused, you can go back to these slides and look at the general guideline. But once the table is introduced to you, it's quite easy to use